Hi. Before we begin, I'd just like to point out that everything mentioned in this video has primarily come from the video I've posted in the description by iGEM. It is my intention to replicate this video successfully and prove to myself that I can run a successful restriction enzyme digest on Benchling, navigating correctly without failure across the basics. So with that, let's begin. Okay, so we have the PCDF1B Titiago plasmid. Today, we're going to be isolating the Thermus thermophilus argonaut gene. I'll be referring to this as the Titiago gene. We're going to be running a restriction enzyme digest. If you don't know what a restriction enzyme is, that's no problem. From what I understand already, restriction enzymes are what are found in bacteria. In bacteria, you have these signatures called methyl groups. So when, say, a virus tries to infect the bacteria, trying to take it over, they're not methylated. So what the bacteria do is that they have these things called restriction enzymes. These are just proteins that recognize if DNA is either methylated or not. But hold on, how does DNA actually become methylated? Well, that's because of an enzyme found in bacteria called methylase, and that's just what makes DNA methylated as it's synthesized. Then, it's also worth mentioning that restriction enzymes mainly only recognize palindromic DNA sequences. That just means that if you have a DNA pattern that looks a little bit like this over here, then you can see that the top half of the DNA sequence is the exact same as the bottom half of the DNA sequence, but they're only mirrored. They still match though. But why that is? Well, I'm pretty sure it's because it's more effective. When you have a palindromic sequence, you only have to make a cleavage point at one site, as opposed to two. If it's not methylated, then the restriction enzyme will go and cleave the DNA of the virus, making it useless. When you cleave DNA, it has the ability to repair itself and put itself back together. What scientists have been able to do with this is that when they cleave the DNA, it creates a sticky end that looks a little bit like this, if you see me in the bottom left corner. So when it's like that, you can see the DNA, well, a little bit of a rough sketch, but it does look like that. Then they can add their own DNA and make it whole again. And secondly, if you don't know what a plasmid is, it's just a circular piece of DNA that's found in bacteria. Get ready to run the digest. We need two different sites for the cleavage to occur. I have the KPN1. As you can see, we have the 4 base pair overhang that I mentioned, which is a sticky end. You've got a GTAC. And like I said, it has in this case, it's this way actually. And we're going to go down all the way to the not one. So it's an opposite thing. So if you took the two there, you've got one like this, you've got one like that. And they fit perfectly together to make a whole. From here, we're going to go up to the button that says digest, and we're going to insert the names of the restriction sites. So we have KPN1, there it is, and not one. So after this, we should have a new tab up here that will say digests, and it'll display the data that we want. So we're going to click run digest, and bingo, we have the digest here, the information. And if we go to virtual digest, then we have this. What this gray box here resembles is just, if you imagine the plasmid that we have, and you've run the digest, so you've cleaved the DNA and you've taken out a sector of that. You've got two pieces now. You've got like a squiggly line that once made up the entire circle, and you have another little shorter squiggly line, which is the gene that we've just taken out. So we have isolated it. So like I was saying, this is a test that's commonly done by scientists. This gray box here is just a piece of gel where both pieces of the DNA are placed up here, and down here you have a positively charged material. Like DNA is overall negatively charged, the pieces of DNA will slowly move closer and closer to the positively charged material because positive and negative attract. Which one will move further? Well, that's because of their mass. The lighter one will move further because, well, of gravity, and the heavier one will not move as far. So, which one's the heavier one and which one's the lighter one? If we look at our linear map, we can see that the Titiago gene is here, and all of the rest is over here. This is much larger than this bit, so we know that this is the lighter and smaller piece. Back to the virtual digest, if we click this, This should be the lighter one because it's moved further. We go back to the linear map. It is the thermophilus gene, which we also see here on our plasmid. And if we click the other one, this should be the rest of it, which is just the larger piece. Back to the plasmid, it's all of the rest. And the linear map, it's all of the rest. A little bit there, just got cut off. So that's a successfully done restriction enzyme digest. Thank you very much for watching. It's my goal for this video for it to be the first of many. So as I grow and this channel evolves, I'll be posting more about science and science-based tools. A note to myself is that in, I don't know how many years, whether it be 2 or 5 or even 50, and I watch this, I might be thinking, what am I saying? This is all wrong. Well, I'll still be grateful, and I'm grateful now, because this is exactly what I need to do to pave the road and take the first step. This is exactly what needs to be done to get there.